So when you're dealing with derivative of polar functions, we still have to come up with the equation of a tangent line, and that equation of a tangent line is going to be in rectangular form, or at least it's thought of in rectangular form. It's a rate of change of y with respect to x, all right? So what we're going to need is an x equation and a y equation in order to come up with the x, the dx and dy part of the derivative model, right? Now, we know from earlier studies that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta. Okay? So we just got to differentiate this. Now, the big question would be, because it's a function of two variables, that's your welcome to Calc 3 moment, I think, you know, because we're going to be dealing with functions of multiple variables very often. I can take the derivative of this with respect to with respect to r or theta, all right? But what we're going to do is take the derivative implicitly, right? So I'm going to find the derivative dx with respect to, and again, it doesn't matter as long as you're consistent. I'm going to do dx d theta and then dy d theta. All right. So this is a product of two functions, r and cosine of theta, r and sine of theta. All right. So when I take the derivative of this, I have to use the product rule. So I'm going to color code first and second functions. I don't need the calculator anymore, so we get rid of that. So first and second functions, and then we'll apply the product rule. So the first function, r, times the derivative of the second. Now, since I'm differentiating with respect to theta, it's just simply derivative of cosine theta, negative sine theta. All right. Plus the second function, cosine theta, times the derivative of the first function. Derivative of the first function, it's with respect to theta. If it were with respect to r, it would just be 1, but it's really just going to be 1 times dr d theta, so I'm just going to say dr d theta. All right. So I'm taking the derivative of the r function with respect to the variable theta, right? And since we don't have a relationship for r in terms of theta, when we get to particular examples, we would just have to leave it at this, all right? The next part, the dy d theta, same idea, first times the derivative of the second. So the first function, r, times the derivative of sine with respect to theta is cosine theta. Plus the second function, sine theta. Times the derivative of the first function. Again, derivative of the r function with respect to theta, dr d theta. All right. So I now have the two bits and pieces that I need in order to come up with the dy dx. I just got to divide them. All right. So that's the key ingredient there. I'm just going to kind of smidge it down a little bit. And I'm also going to get a little selfish here and make this dy dx equals, but then I'm going to do a little copy paste job. Here's my dy d theta. I'm just going to put it over here. I'm going to leave a little gap. I'll show you why in a second. All right, so dy dx is going to be equal to the dy d theta divided by dx d theta, which in turn is equal to that whole expression. All right, that whole shabiggity bang. Now, you kind of look at it and say, well, I don't know that I want to leave it like that. It's kind of messy, but you know, it's a matter of preference, right? So you could try to clean it up, but I don't know what benefit it would give. It would be to do that. But you can see in this complex fraction, I'll just circle or box it here. We have dy d theta over dx d theta. That's not a box. We have a complex fraction with a common denominator. So those d thetas are going to cancel away and just leave you with a dy dx. Right? So that part's okay. It's the right-hand side of it that just became fairly monstrous and hideous and ugly. And it's like, oh, what on earth am I supposed to do with that? Well, it's just a rule. If you look at the first example below, which we're not going to do now, I'm going to save it for next class, we're going to see that we have a whole lot of things that is ready to be plugged in, right? You see, write the equation tangent line for r equals 1 plus sine theta, right? So now, right off the bat, I have something I could substitute in for r. Replace all the r's with 1 plus sine theta. Then I have cosine theta, sine theta, and also dr d theta. Well, I could figure out dr d theta. I have an r in terms of theta. I just need to take its derivative. That'll give me a cosine theta. So I can plug that in for all my dr d thetas. So I'm good there. And then it even tells me what theta is. So then replacing the r with a 1 plus sine theta, and then replacing the dr d theta with a cosine theta, and then replacing all the thetas with pi over 3 would allow me to come up with the computation or compute the value of dy dx numerically, right? It's knowledge of unit circle again, but it's all there. It's all kind of splayed out for you, all right? So I'll make this optional. I mean, if you want to try to tackle it before next class, you're welcome to do it, because at this point it's just substitution. But like I said, I'm going to take this one from beginning to end next class, all right? So, but I wanted to give you a little bit of a preview because this is really it for polars. Next time we're going to get, we'll finish up all the stuff I said we were going to finish up, but then we're moving on to vectors and vector operations. So we don't have really too much to go in the unit for a couple of reasons. One, because there really isn't too much left to go in the unit, and also because there can't be, because the test is coming up. All right, so if you haven't taken a look at the review problem sets for that first unit test, I'd give that a look, because we're getting closer and closer. All right, so definitely worth your time. All right, so let me stop this recording.